So we wait. Ashok is coming. This is warming up. Is it working? Okay. Shall I start? You can start. Yes, you can start. So, good morning, everybody.
Good morning, sir.
I've been asked to start, so let's start the morning, the third of these days. So I hope you enjoyed already the last 2 days. I think there are lots of new things coming in, and I looked at it also sometimes by the internet, and it was really tough sometimes, but it's full of information. That's the interesting part. You heard about electrophoresis already. You know probably about electrophoresis as well. I will bring you in the world of capillary electrophoresis, which is a method we use sometimes right now, a little bit more even. And we use a lot in the 90s and beginning of 2000 for separation of compounds. That time I met actually Ashok Malik, and that's the start actually of our cooperation, why I'm here in India now, right, and meet you and able to communicate with you. So thank you for being here. So my name is Philipp Schmidt-Koplin, actually, I'm French. I'm working in Germany since 30 years at the Technical University in Munich on one side, and at the Helmholtz Center in Munich on the other side. I have a background in organic geochemistry, agronomy, and went into analytical chemistry very rapidly for the characterization of these complex materials. It's brown material out there, these organics. And for that, we needed different techniques. And actually, I wanted to tell you a little bit about that. So that's a technical university where actually I'm associated at the chair of analytical food chemistry. So that's actually the topic we are following there at university in Munich. And we work on food metabolomics, so profiling of metabolites in foods. We're interested in nutritional aspects and work with microbiome. So it's this part that is covered actually in the project we have at university. And actually, main of my time is at the Helmholtz Center in Munich, which is actually in the northern part of Munich, 30 kilometers from university. And there it's the analytical biogeochemistry. See, it's combining biology and geochemical aspects in analytical chemistry. We have a move right now. We move into medical sciences. And what I'm following up there is actually related to the work at university, aspects of nutrition, microbiome health. We look at the impact of some nutritional aspects on health and going metabolomics as well. I will tell you what it is in these studies. So important is to see that we're profiling the chemistry. So it's the chemical continuum from the chemistry of food, its transformation in the gut, and the corresponding metabolites in the body fluids, and how is this affecting actually, and how is this changing, and how these profiles are changing in human beings or model animals during different stressors, during nutrition stress, for example, or environmental stress. So actually food is, it's not, yes, it's working on. Food is actually, we have nice fruits here. I really enjoy that. And if you look at the chemistry of these foods, it's the chemistry of biology you're following. Yeah? All the metabolites you see there are involved in some kind of metabolic network in a living system. So governed by the enzymes, means proteins, governed by the genomes actually of these foods at an endpoint. So you have all these ladders in omics as well to consider. This is typical Bavarian here. Yeah. Schweinsbraten, Knödel, Haxe. That's pork which is roasted. If you roast something, if you have a heating of something, you have transformations, you have chemical transformations, and these transformations are leading you to a diversity of compounds that certainly are much, much higher you have in biology. These are abiotic processes. Same is for the roasting of coffee down here. The browning of coffee, Maillard reactions, giving the flavors, giving the color. These are chemical reactions which have nothing to do with biological processes. So on one side you have biomes, on the other side you have abiomes, and that leads to the complexity of this chemistry. If we look at the signals we get out in mass spectrometry in living systems, about 10% of the signature is found in databases, 10%. 90% is just unknown. So how to deal with that? That's the problems we have. That's the solutions we try to find in terms of analytical techniques, in terms of characterization techniques, in terms of bioinformatics, in terms of artificial intelligence used to process a lot of data in this field. The other side, we have these non-enzymatic processes. There's no database on that. So everything needs to be taken under scratch. And looking at the whole environment, so this holobiont, these interactions of microbiota with the host, can be human, can be dog, cat, can be mouse, can be C. elegans, little worm, can be flies, can be many organisms, but it's also always an interaction between microbiota, which are associated to these organisms and which are contributing to metabolism in a way and a degradation of this compound. So that's the frame, and that's the frame in which I'm working. But how to deal with this diversity? We'll speak about capillary electrophoresis now. No hurry. But capillary electrophoresis is a little tool, part of a whole zoo of instrumental approaches. We use metabolomics. Maybe you have heard about that. Metabolomics is a tool, it's a concept, it's an idea that came out actually in the end of the 90s. Jeremy Nicholson put this word actually in the community. End of the 90s, he's an NMR spectroscopist. So he's making NMR, measuring body fluids with NMR, and trying to get as much as possible information out of it. And the definition of metabolome, of the metabolomics and of the metabolome is it's the quantitative analysis or description of all low molecular weight metabolites in specific cellular systems. You have a quantitative aspect and all. After all, I told you before, very difficult. That's hundreds, thousands of compounds. It's really highly complex and diverse. So how to do? Well, from the definition and from the side of NMR, all good. It's quantitative, and you see everything which has a proton. Here's on the good side, and that's definitely a way where you have an integrated idea of your sample. If you go in with mass spectrometry, or if you go in with chromatography techniques or separation techniques, you have a bias given by the technology you use. So you always have to be aware of these situations. So just to go on, we have different ways to go. We have a more targeted approach. That's the guy who was looking in his glasses. Yeah, he's targeting a star, and he's looking very detailed in this star, and you will be able to describe it very detailed. We'll be able to make quantitative analysis if needed, or some spots or whatever he sees there. But he will miss everything around. Then you have the other approach, which is the non-targeted approach, which is more discovery-oriented, which you use tools which may cover a lot, not necessarily everything. Well, NMR is covering everything. But then you have a problem of resolution. How much are you able to see in there? So ideally is the resolution of the guy who's looking in his glasses, but covered all over the space, which is a little bit difficult to go. That's now where I come to separation techniques, spectroscopy and spectrometry, where CE has a little place in there. Yeah? Because in this approach of chemical analytics, you combine technologies. Yeah? You combine LC, you combine separation techniques with detection, which is spectroscopy maybe, or mass spectrometry. And each individual branch here has its own technologies. And all of you here, some of you are using some of these technologies and developing these technologies. You had the talks on microtask this week, where also you have separations aspects. That's a little part of it. It's contributing to the whole zoo of instrumental, which is possible. So in terms of chromatography, starting with increasing resolution, following the arrow, we have paper chromatography, thin layer chromatography, solid phase extractions, flash chromatography, column chromatography, where you're able to separate fractions and you have a given resolution with that. An increasing resolution is going into instrumentation like LC, ultra performance LC, different CC, GC. CE is part of that. It's one dimension. You can combine dimensions, as you can combine dimensions in CE as well, to have two-dimensional issues, which is improving you the amounts of compounds and the resolution of what you can see. So that's actually how it processes up to 3 or 4-dimensional separation systems. At-line or online to some detection methods. Yeah? The question is, how much resolution do you need? You don't need to go in and have a development of all these different dimensions. How much do you need for your project? Thin layer chromatography may be just sufficient. Or do you really need to have 3-dimensional separations to have the purity of a compound, really pure compound that needs to go ahead with? And what's the resolution in there? So that's always the question, what is needed? And very often, money is limiting you that, and time is limiting you that. Yeah? In terms of mass spectrometry, similar. You have quadrupoles, triple quads for quantitative analysis. It's great with the resolution it has, and the techniques are adapted for that. Going up to eye mobility, going up to QTOF systems, to Orbitraps, to FTICR, FTMS. You can couple that. Spectroscopy, similarly, in terms of whiteness and description of the space. One-dimensional systems, spectroscopy system, fluorescence, UV, infrared, going to NMR, 2D, multidimensional NMR, and combinations of these technologies, as you can see, because if you make LC-MS, you combine LC with MS, or it's always a combination of tools which increase you actually, ideally, the number of compounds you potentially can see in your sample. The question, however, is always, what is needed? Thank you. What is needed? Do you need an LC-MS with a quadrupole, or do you need an LC-MS with a QTOF, with a high resolution? Do you really need an Orbitrap, an FT coupled to that? Where at the limit, the project will give you the answer, and the time, money, and all the surrounding will give you this answer. I resume this in this paper. Just feel free to send me an email, and I can send you the papers accordingly. And if you have questions during the talk, please go ahead and ask the questions. We'll get some kind of dynamic. It's better for me than having a lecture. So that's the concept, that's the frame. And in this frame, CE here has a little space, but has a space because it is very particular in its separation mode and is touching some metabolites you may not or hardly only separate with other technologies. So it has a niche, which was established in the 90s, beginning of the 90s, and which has a revival now because it may be very competitive to helic type of chromatography to measure polar components, or components which are ionic and which are of biological origin. Here we may use CE for metabolomic approaches when coupled to mass spec. I will show you examples. So that's for the introduction. Let's come to CE. This course, I did it for a long time, and I'm always adding new things in. There is nothing new in inventing electrosmotic flow in the last 20 years. It did not change much. Yeah? It's the same principles. What you will see also as pictures, as ideas, concept, it's mainly taken from this book here, where I'm glad to participate since many years. We started with German, big book, which you find in all classes in university and analytic chemistry. You will find everything on proteomics and mass spectrometry and spectroscopic methods, etc. Very nicely presented and very educative. And here's a chapter of that. And there is an English edition as well. You may find partially this on the internet. You have to check. I can send you the chapter if you would like to. So that's one side. And the other thing is over the years, I did my PhD on capillary electrophoresis. That was beginning of the 90s. That's quite some time ago. And I will show you a little bit what I did there, because it's still conceptually. I want to bring you concept ideas, not methods necessarily in detail, but to bring this capillary electrophoresis in its context. That's the idea. And out of this expertise, and book came out where Ashok is involved as well, with a few chapters with his expertise. That's at that time. And again here, some chapters may be interesting for you. I can send it to you as PDF. Just ask me for that. Historical. Well, this is European history. Yeah, you may recognize or not. Just this guy in the middle here is called Napoleon. He was the emperor in France, and he had a big conquest in the 19th century all over Europe. And so he was really an emperor. And this emperor is here in contact with a scientist who's presenting him something. And this scientist here is called Volta. Volta? Well, the name says already something. Yeah, it's the start of electricity. Yeah, what's happening? Yeah, people were discovering what's going on. Yeah, and what does it mean? Yeah, and we're experimenting with it differently. And that's actually the first battery he was showing to the emperor. That was beginning of the 90s. That's quite early. That's quite some time ago. But if you think that that's the basis of our communication now here, it's just amazing how it evolved. Yeah. And now everybody of you has a handy mobile and can have access to everything. It's all based on electricity, and that's where it started, somehow with many other scientists. Yeah. But that's the basis of capillary electrophoresis as well. Setting up a voltage, and in this voltage, in the capillary, some stuff is happening. And this stuff that is happening, that's what I want to discuss with you today. So it's Alessandro Volta, Italian guy. That's his pill, his battery, yeah, which was presented. Many pictures on that. That's another pictures representing this discovery. And 1808 already, some experiments were done with this battery. And Royce described that and described the basis of electrokinetics. You heard about electrokinetics as well in the microtask, because it's a way to load samples or to move samples in the system. Well, that's what he did in 1808. He put these two electrodes, these two parts here of cover, and put them in a clay water suspension, and he saw movements. And that's electrokinetics. So he described it already very early. And that's even here published. They published this guy that time. They published and then they argumented and write each other. I'm against, I'm for it, and whatever. And it was a very fascinating time that time. Different than now, where everybody is writing his paper and having his impact. That time it was a scientific discussion. That's important, scientific discussion. Going on with historicals, we got a Nobel Prize based on electrophoresis. Did you know that? It's Tiselius, and that's his apparatus here. He made actually a U-tube, yeah, with some electrodes. That was 48. That's closer, very close. And he did some electrophoresis of blood plasma, yeah, of human plasma. And he separated proteins. With this system, he got the Nobel Prize sometimes. And that was a huge discovery and the start of people thinking about using this process. And that's where we are now. We do it in microchannels. You saw this these days. Just amazing how that changed and evolved. more modern in the 60s, were the startup of 2D gels. So based on principles of size and isoelectric focusing, you separate your proteins on your gels and putting as well some potentials and having electrokinetics in there. And more recently, in the 2000s, having high resolution mass spec at the end as a detector, having information on masses of charge distributions in these masses, on structure information, even though at the mass spec with all the experiments you can do, if you have a separation in front of isoelectric focusing, as done in electrophoresis, capillary electrophoresis, if you couple capillary electrophoresis to this mass spec, you have a two-dimensional plot which is corresponding, like for the gel, to an isoelectric focusing, separation, and a mass separation. So it's very similar. And you can do this in the generation of a lot of data you have to process, but you have one information in one slot. And you can repeat this, ideally. Reality is that it's always reproducibility is always a problem. You just have to reach the statistical endpoint where you can work with. So that's for the history. This is another history in my life. She's called She, and She is my electrophoresis system. I was working in the 90s, the beginning of the 90s. I still have it in the basement. It's not used anymore, but I keep it. And it's a Beckman system. And actually, we were coupling it to UV fluorescence and mass spec and conductivity and so on and so forth. And Ashok was working on it as well. More recently, it's Agilent that take over this market for scientific instrumentation in CE. We saw many applications, dedicated applications of these instruments in many fields. Yeah, and genomic at the beginning was a gel separation of the strengths. Yeah. Now everything's automated in other ways. But the research instruments, actually, that's actually the system we have, and that can be coupled to mass spec. And that's the kind of mass spec we have with, in addition, high mobility in front. It's a Q-TOF, so that's actually the way to go to have separation coupled to spectrometry. But let's come to CE now. Actually, it's very simple. And you will see it's really simple. Yeah? It cannot be easier. Yeah? It's really easy. It's a tube. Yeah? It's a tube which is filled with a buffer. And all the dimensionalities, all these dimensions are important for sure. And so it's a tube which is empty first with air. It's fused silica, which is conditioned to get a good surface charge, conditioned with pH, with alkaline solutions, water solutions, natural washed with water. And then it's filled with a buffer. And then it's injected with a sample, and then some potential is applied, and something is happening in there. And it's something, that's what I want to tell you. It's something you can orient it, you can use it, you can model it. Usually the capillary length is 20 centimeters to 1 meter. Its inner diameters are 50 micrometers to 75 micrometers. The injection is done hydrodynamically. So it's like a tube you put in water, and by pressure, the water is coming out. For people who have aquariums, who are emptying water from some bigger container, that's what you do actually. You use this pressure. It's not different here. Either you apply a pressure, or you use the height to inject little volumes in your capillary. The voltages around are between minus and plus 30 kilovolts, sometimes even more. And pH range 2 to 12. Yeah. You also have extremes in some cases. You can use aqueous, non-aqueous. That's just the frame in which we work. And then you have a detector at the end. Well, you can think about any detection, and with a little fantasy, you will find and invent a new one. People just tried many things in this field. So C14, isotope detection, whatever, it depends on the project. People will just have fantasy and use it to find solutions to their problems. So it's optical, the most routines, UV, indirect UV, laser-induced fluorescence, for example, chemoluminescence, can be electrochemical, and can be mass selective with different ionization methods. So all is open, depending on the use you have for this technology. Just to make the link with old pictures on what you saw this week with the specialists we have in room. That's miniaturization of that method. You saw something, and we'll see some issues this week during this time as well. And actually, that's just a miniaturization of the concept, where again, you can, with all the advantages of miniaturization, you can go down in the time of the separation. Yeah? Then detection becomes a problem. Yeah, but that's just a separation which was done maybe 15 years ago already, which is such technology. I told you my transparencies are old but still actual. I put new things in as well. But that was the beginning of that, maybe 15, 20 years ago. Dimensionalities. Can you imagine dimensions? I mean, from what sizes are we speaking? I'm speaking about a column which has 20 centimeters to 1 meter, which has an inner diameter from 50 micrometer to 100 micrometer. What are these dimensions? How far is it from here to your home? How many kilometers do you have to your home? 8 kilometers, 10, maybe 100 dimensionalities. How far is it to the moon? Who knows how far is it to the moon from here? Just to speak about dimensionalities. How many kilometers are to the moon? You certainly, if you drive a lot, would manage to go there. It's about 300,000 kilometers. That's not too much. That's not too much. But dimensions, yeah? In our head, what are dimensions? And definitely here we have in a system of 50 centimeters in length, of 50 micrometer inner diameter, we have a volume of around 1 microliter. 1 microliter, that's imaginable. We had these pictures yesterday or the first day already from Roseanne. You remember that. We speak about microliter in total volume of the column, and we speak about nanoliters when it comes to injection plugs. Can we inject maximum 10% in volume in this capillary? And the lower the better, keeping resolution and movement of the ions in the capillary. And this is in the nanoliter range. We will see the numbers later. And if you make some upscalings, I don't really like to do it, especially with the specialists in the room, because they will criticize it. But if you make a mind upscaling, simple mind upscaling, and put this dimension to a tube, you know the tube you take, which has 1 centimeter in diameter, that's if you're in your garden, or the tubes you use at home. And with 1 centimeter in the ratios of the volumes and the lengths, it would be a tube of 100 meters, and you would put 80 liters in there. That's a dimensionality I'm speaking about. But in our world, in capillary electrophoresis, will be in this little tube. Okay, so that's the status, very simple setup. From here, we will now see how we can inject a sample, how we can make separations, and how we can handle this. What are the possibilities to handle and have selectivity in separation? Or all the way around, what reactions can we induce in this separation buffer to selectively act and affect the mobility of these ions in the system and thus affect separation? Or have information on interactions? Depends on where you come from and what you want to do with. So one possibility is the hydrodynamic injection, which is the most used actually. And what you do here, you have your column and you apply a pressure on one side. And the column volume is in a microliter range, the plug of the sample is in nanoliter range. So you apply actually a pressure on one side, and it's this difference in pressure across the capillary which will enable you the liquid to be pumped in, to be pushed in,
and certainly less depending on viscosity, which is temperature dependent, etc., etc. So you have to consider that. And what you do, you don't know the volume what is coming in. You have to calculate the volume that is coming in, because you apply a given time in a given liquid, a given pressure, and that's corresponding to a volume, and that's what you can calculate. Just as an example, an injection of 10 seconds at a given pressure for columns which have different lengths, you will have, according to the same injection time in the same system, you will have different amounts from 16 nanoliters to 160 nanoliters, depending on the capillary length, depending on capillary length and the inner diameter. So that's actually some very practical results where you see that both length and diameter have an effect on the injection volume and the size of the plug in your capillary. So you're feeling like this for 1 to 10% of the capillary, applying the same pressure, the same time on these different capillaries. So you have to know these rules to navigate and to be sure in what limits and what you really inject and how much. So that's the 0.5 psi injection, which is done in this case. You also have the possibility to apply a voltage from the start between the two sides of your capillary when it's plunged into, when one side of the capillary is plunged for the injection to the sample as well. And doing so, you will have some electrodynamics, which is the electrostatic flow, which is bringing you and sucking you some sample in, and ions can move as well depending on the charge and the size. And let's come to the electrosmotic flow. In fact, these are pure silica capillaries. So on the surface of this capillary, you have silanol groups, which are more or less ionized depending on pH. So at high pH, fully negatively charged surface. At low pH, protonation, you may have neutral surface. And I told you it's important to wash the system before and to condition the system before. So regular, very tedious, regular washing and conditioning of this capillary is needed. So washing with high alkaline solutions, neutralizing, putting solvents over, putting water again. There are different procedures, but what is important is to always get the same surface condition of your capillary to have reproducibility in time. So what's happening here? You have a charged surface, and on this surface you have the corresponding positive ions, which are in contact. And you have different models, like Helmholtz capacitor model, probably the simplest one, the GUI, diffuse model layers, or the Stern with a couple diffuse charge and a drop of potential. So you have a potential which is different in addition. What's happening actually is when these cations, which are actually in the solution and which are on the surface of that negatively charged wall, when you apply a difference in potential, they will have the tendency to move along the surface, and this is what is called electrosmotic flow. And that will generate actually a flux of all the liquid in the system, which, if the surface charge is highly negative, means at high pH, you will have a lot of cations on the surface, you will have a flow which is much higher, and at low pH, actually, when you have rather protonation and not much cations on the surface, this electrosmotic effect will be very, very low. So it's really in the nanoliters per minute or quasi-zero. So you can handle the speed of the flux of the solution in the capillary as a function of pH, simply by changing the pH. And you see here as well that other effects comes in. You have viscosity, which plays a role. You have, which is temperature dependent. You have the ionic strengths as well that can have an influence on that. And that's different parameters you can use, though, in the adjustment of your solution to manipulate electroosmotic flow. Yes, so that's what we have here again, and yes, not more to say. It's a pH dependency, ionic strength dependency, temperature dependency, and you can. It's an experimental setup where you need to test that to have it in your feeling and in control at the end. The advantage of that movement of liquid in the capillary by application of a voltage. So the higher the voltage, the faster, enables you to have in opposition to a pressure that is applied on the capillary, where you have this hydrodynamic plug here and this diffusion on at the detection level at the end with broad peaks. You don't have this peak broadening so far, you just have the diffusion, and you have very sharp lines. You have a very high resolution actually at the detection, and that's also gives you this low dispersions which are happening. So you have a very sharp line actually in the separation. So what you can do is actually, instead of having an injection with pressure, as I told you before, you can have your capillary in your sample at the given pH, applying the voltage, and then there will be the movement, electrosmotic flow in the capillary, which will move you some solution in the capillary, in addition to the fact that the ions at that pH of the sample will also move or be kept outside the sample bladder. So that's also selectivity you can handle at this level. Just as an idea, here, because that's one thing which makes it different to chromatography. And you had courses of chromatography also yesterday, and probably you use chromatography. If you don't change each time your buffer, if you don't take all the time the same external buffer conditions, and you make 70 times measurements with the same buffer in the vial, you will have ion depletions, you will have an acidification of your buffer because of the moving ions, and you will have other AOF. You will have all these problems in changes in AOF and changes in retention time. And this is what is shown here. In this time scale, these two components, they're just moving along, and you would not be able to compare it anymore. But in calculating the effective mobility scale, they're still superimposable. So even in these extreme conditions, you find actually the possibility to normalize and to position. Because you look at the absolute speed in the train, so in the capillary actually. That time I was working with organic matter from soils, waters, etc. So ugly mixtures in a gradient and continuum of charges, in a continuum of sizes, highly diverse systems. And that's a type of electropherogram which was shown, which I had in time scale. Yeah? So you had peaks here very broad, you had peaks very sharp, and it's a combination. You really don't understand what's happening. And when you put this in mobility scale, actually that's how it's looking like. It's a complete different shape. Yeah. So the compounds which are very broad at the end, that's the high speed runners that goes to the opposite, which takes a lot of time in front of the detector because they are moving in a speed very close to the AOF, and you see them actually as a very broad peak in time scale. In mobility scale, they will be as sharp as any other. Yeah, that's what's shown here. The 3 here is as sharp in mobility scale than the 1. It's exactly the same. And because that was of interest that time, because that showed you the diversity of these mixtures in terms of oligomers and polymers. But in mobility scale, we were able to compare different pHs, different ionic strengths, just in comparing this effective mobility scale. What are the direct effect? You can calculate. You can simulate. Did this with Excel, and let's just imagine a constant voltage, 25 kilovolts, in that constant length of the capillary. And this is the time of DOF down here. The higher the time of DOF, the slower the speed in the capillary. The lower the time of DOF, the higher the speed in the capillary, because the neutral compounds will go very fast to the detector. And that would be the time, just taking a time, of different analytes which have different charge to mass ratios. Think about benzoic acid, 1 carboxylic group, phthalic acid, 2 carboxylic group, trimellidic acid, and the 4 carboxylic groups. That's actually the ones here. And they have very low and very high effective mobilities. And the ones which have very low effective mobilities, which are very slow actually in this tube, coming slowly to the detector, they will come very close actually to the DOF. You will see them. The ones, however, who are very fast, running to the opposite, moving to the opposite, like the triply or quadruply charged compounds, depending on the speed OF, if the speed of the column is too small, in the column is too small of the buffer, they will go out the other side. You will not even be able to see them. Yeah? So depending on the setup, you won't necessarily see everything in your system. And that can be modeled in all directions, just to have a feeling of the limits and the possibilities of the space you are looking at in the conditions you are. So what are the compounds you can see in your system as a function of the speed of your AF? Because this is determining actually the possibility. Same here. That's how it looks like. You have time scale. You have, on one side, you have the EOF, which is coming out here. So after 10, 11 minutes, you have the neutral compound that comes out. That gives you the speed of your buffer in your capillary, in your tube. Compound 10 here is actually a compound that takes much longer to come out, goes to the opposites. These are anions. In front here, you have cations. And you see that that compound 10 is very broad, and the cations here are very sharp in peaks. But if you convert all this in an effective mobility scale, the peaks have the same width. Yeah? I mean, these are all components which have the same space in this capillary, which are moving a different direction, and there's little diffusion. Same here? Okay. Yeah, and that's already at zone electrophoresis. Have questions on that?
What is CZD?
Capillary zone electrophoresis. Yeah. So it's a zone electrophoresis. It's called, that's the method, how is it called? And then you have different other possibilities I will go down in a moment. Other things here is, yes, charge is important, size is important, frictional forces are important, and that will drive actually the speed of the analytes in your system. So what's the structure dependency, analyte structure dependency in the separation in C? Well, that's where we come on frictional force. You have a charge issue, which is important, and a frictional force. And that's actually charge and size. But size is relative. How can we model a size? Yeah, and here different aspects comes in. All the principles of mobility and potentials come in. Of zones, viscosity has an effect on that, definitely. Radius has you can assume different geometries of the particles as well, which will have an effect on that. The charge of the analyte will have an effect also on its surrounding layers And that all will affect actually the movement of the ions in solution. Practically and empirically, many models were started to go. And that's the state of the art I was using at that time, and which is very practicable. You will have modelizations during the giant project where people will go in detail in that. But that's the models that were existing at some point. Charge parameters modeled from pKa's, which are known or that can be calculated for unknowns. Size parameters, different ways to calculate, things to consider. The simplest is the mass, and based on mass, different models were set up for peptides. Many papers came up on that at the very beginning of CE. And I was looking for something very practicable. And the most practicable for me, definitely, was a model where I projected the measured effective mobility, so this speed, effective speed in the capillary, to a charge to size ratio, so to a charge to mass to third ratio. That showed me the best linearity, taking different type of compounds I was interested in at that time, which were aliphatic acids, different type of phenolic acids, and this cross pH, so measuring cross pH. We'll come on this right now, how this was generated. So that's behind. So we say electrophotic mobility is directly related to the charge and the size, modeled as mass 213. Like this. Based on that, means we have the possibility, having the charge from the pKa and the mass of the compounds, to follow up actually the mobility as a function of pH. And looking at this, you have compounds which are singly charged, so carboxylic acidities with a pKa around 4 to 5. They're neutral at 2, they won't move, they move with the AOF. If you increase the pH, they will be partially charged past the pKa, and we'll have one charge around 6, 7, and then they have the continuous charge all over the time. Means their effective mobility will move actually adequately and will be very similar. If they're doubly charged, that's the other line. Triply charged, that's trimylitic acid, and here pyromylitic acid. 2, 3, 4 carboxylic group on one aromatic. That's how the mobility would be as a function of the different pKa's of these acids. If you have compounds which just have a phenolic group, phenol, then they will be quite neutral all the time, and at the pKa around 9, 10, they will start to ionize, and they will move out of the system. Why I'm showing you that is that actually the behavior of the ions, which are dependent on their charge, you can put models on, and you can use that. And what I wanted to do at that time is to differentiate compounds which have different type of acidities, means different type of functional groups which are contributing to a charge. Means here carboxylic acids and phenolic acids. So measuring at different pH, these components enabled me actually to differentiate components of different structure. So I could have a structure information in the separations I had. Same can be done here. These are some triazines, metabolites from atrazine, hydroxytriazines with different functional groups here, which may be different methylated, ethylated, isopropylated, carboxylated, and kind of combinations. And depending on the type of functional groups, here you will have different pKa and pKb, means capillary zone electrophoresis is good to separate these components. On one side as cations, on the other side as ions. And that makes it interesting. So we can use pH to selectively get and fish out stuff. And that's the pH range. If I take the mixture I was showing you, and I'm going to low pH, they will be separated here. That's the mobility scale. Yeah. They will be separated as cations. Then increasing the pH to the right, they will lose their charge At some point, they will be neutral, so they have an isoelectric point. Remember that. And at some point, the negative charge will start, structural dependent, depending on the functional groups, and these components will start to be separated, as you can see here. So I've got them separated here as anions, and I've got them separated here as cations at low pH. Means, let's go even further. I can make a model on that. And knowing the mobility of some compounds, and knowing the models very simple models I was showing you, very simple thinking, I can calculate back pKa's. So having an unknown and having a gradient of pH in a measurement, I can calculate back pK and can have a structural information on that unknown. And that's what we did. Well, to be honest, we tried to do it at the beginning, and we very rapidly noticed that there are lots of isomers, tautomers, micro pKa's, and that the pK we see at the end, we can calculate as an average over those features. But that was another result than we were able to show. So that's for capillarity zone electrophoresis. So you know it. You have a buffer, change pH, you change behavior, and invertedly you can, by using and changing these parameters, get information on structures, on these components if they are unknown. Different application. I spoke about organics. These are inorganics. Very early people started to make separations on that. So you have a lot of stuff in the literature where people try to the extreme to use this technology to what can I do with? Yeah, that's a scientific motivation as well, bringing to the edge. Yeah, maybe to learn something out of it. Sometimes it's a road without end. Sometimes it stops very rapidly. But many things were tried in this field, like here as well. That's just applications. Yeah? And having some complexing agents in the buffer also enables you to selectively distinguish mobility and act and modify the speeds of these ions you see at the end of the detector. Small acids, that's methods which are still very used and even routinely used. Yeah, in wine sciences, small acids are measured at that. I think we have to think about the metabolomics because that's compounds of interest. Yeah. So we are now setting up CE again, and we come back to methods like this, which may be robust enough for the measurements we do. That was capillary zone electrophoresis. Questions on that? Because I will move now on. We can have a cup of tea. We have a cup of tea. We have a cup of tea. Sorry for the intermezzo. We have a cup of tea. You may have a cup of tea as well in your rooms.
I haven't put the links that you were Mr. Mobility scale.
Sorry?
I haven't put the link that you have yet in my brain that you were Mr. Mobility scale.
Yeah, I did this very early too. I really got in trouble with it.
It's one of those things that should have called on, but I think it's just people struggle with numbers. That just
It's so amazing. It's so simple. I went to back now. All three. We have to wait. I haven't shown them. Actually, when you go into quantification, you have relative standard deviations of 1-2%. Over the time, you have a decay. But it was reduced. So actually, based on communication, I think that was really Many years, we did experiments that the 60 and 70 measurements of row, show, and put this image together, and then it was accepted. But it was almost never successful. In many application papers I have, with sugar acids and stuff like that. But even in the cases, I always have the moment because sugar acids, which are doing experiments, they're going very rapidly, and it's really very clever and using gold piece and that. And quantification and that was never seen. And then search came with Laurent all the consortium of European standards, and they came up with a solution for CD, which is and I was here.
We've done this before.
We even have the cover of the kids of a journal, which was a team thinking.
But it's, time needs to be right, but people really, really struggle, I think, with the fundamental mathematics. And once they,
Yeah, but here they come even more, here they come from. And what is it?
हाँ देखना इनको चलाया नहीं हुआ इन्होंने एम रखा हुआ
ਸਰ ਮੇਰੇ ਖਿਆਲ ਨਾਲ ਨਾ ਇਹਨਾਂ ਨੇ ਇੱਕ ਵਾਰ ਚਲਾਇਆ ਸੀ ਤੇ ਸ਼ਾਇਦ ਪਤਾ ਨਹੀਂ ਸ਼ਾਰਟੇਜ ਹੋ ਗਈ ਸੀ ਤੇ
ਉਹਨੇ ਪੂਰੇ ਤਾਂ ਨਹੀਂ ਨਾ ਇਹ ਪਤਾ ਕੀ ਚੱਕਰ ਹੋਇਆ ਮੈਂ ਤੁਹਾਨੂੰ ਦੱਸ ਦਿੰਦਾ ਉਹਦੇ ਕੀ ਹੈ ਇਹ ਜਿਹੜੇ ਸਵਿਚ ਨੇ ਨਾ ਇਹਨਾਂ ਦੇ ਇਹ ਹੈਗੇ ਨੇ ਇਨਵਰਟਰ ਤੇ ਜਿੱਥੇ ਚਲਾ ਰਹੇ ਸੀ ਇਹ ਚੱਲੇ ਉਹਦੇ ਉਹ ਜਦੋਂ ਮੈਂ ਦੇਖ ਰਿਹਾ ਤਾਂ ਇਹ ਤੋਂ ਜੋ ਵੀ ਕਰਦਾ ਸੀ ਨਾ ਹਾਂਜੀ ਕਰਦਾ ਸੀਗਾ
ਸੋ ਸਾਰੇ ਲੋਕ ਦੀ
ਉਹ ਜਿਹੜੇ ਆਪਾਂ ਨੇ ਨਾ
ਹਾਂ ਸਰ ਸਾਰੇ
ਕਰਦੀ ਹੈ ਨਾ ਇਹ
ਹਾਂਜੀ ਸਰ
ਗਲਤ ਜਗ੍ਹਾ ਤੇ ਲਾਈ ਇਹ ਇਨਵਰਟਰ ਤੇ
ਸਰ ਨੀਚੇ ਹੋਏਗਾ ਕੁਝ ਉੱਪਰ ਵੀ ਨੀਚੇ ਹੋਏਗਾ
नीचे
नीचे
और इधर नहीं नहीं चलती वो स्विच चलता नहीं है मतलब
ਉਧਰ ਨਾ ਲਾਓ ਜੀ ਉਹ ਸਾਰਾ ਹੀ ਸਿਸਟਮ ਉੱਡ ਜੂਗਾ ਇੱਥੇ
ये चलता ही नहीं स्विच नहीं
ਇੱਥੇ ਲਾਓ ਨਾ ਹੋ ਗਿਆ ਨਾ ਕੰਮ ਅੱਛਾ ਇੱਥੇ ਤਾਂ ਭੁੱਲ ਗਏ ਵੀ ਨਾ
ਇਹਨੂੰ ਬੰਦ ਕਰੋ
ਬਸ ਇੱਥੇ ਨਾ ਲਾਈ ਜੀ ਉੱਥੇ ਲਾ ਦੋ
ऑन करो स्विच ऑन कर दो तो पावर में
ਬਸ ਚੱਲ
अच्छा वो शॉर्ट है भाई अंदरों
ਸਰ ਅਸੀਂ ਸੋਚਿਆ ਨਾ ਇਨਵੇਟਰ ਤੇ ਨਾ ਹੋਵੇ ਤਾਂ ਕਰਕੇ ਅਸੀਂ ਉੱਥੇ ਲਾ ਦਿੱਤੀ
अच्छा ये लग लगे है ये वाला इधर लगे है मैं कहते ਉਹਦੇ यूपीएस ਤੇ ਪਾਇਆ ਸਾਰਾ ਚੱਲਿਆ ਨਹੀਂ ਭਾਜੀ ਉਹਨੂੰ ਛੇੜੋ ਐਵੇਂ ਕਰੋ ਮੇਰੀ ਗੱਲ ਸੁਣੋ ਆ ਜਿਹੜਾ ਯੂਪੀਐਸ ਵਾਲਾ ਸੁੱਚ ਹੈ ਨਾ ਇਹ ਚਲਾ ਲਓ ਇੱਕ
ਯੂਪੀਐਸ ਵਾਲਾ ਕੱਢਾ
ਨਹੀਂ ਕੱਢਿਆ ਨਹੀਂ ਹੋਇਆ ਭਾਜੀ ਆ ਦੇਖੋ ਇੱਧਰੋਂ ਯੂਪੀਐਸ ਚੱਲਿਆ ਨਹੀਂ ਨਾ
ਚੱਕਰ ਕੀ ਹੈ ਇੱਧਰ ਤਾਂ ਲਾ ਦੇ ਸੁੱਚ
ਔਰ ਔਨ ਲਾਈਟ ਨਹੀਂ ਨਾ ਇਹ ਵੀ ਆ ਕੱਢ ਆਪਦੀ ਤਾਂ ਕੱਢ ਉਧਰੋਂ
ਚੱਲ ਪੇ ਚੱਲ
ਨਹੀਂ ਚੱਲ
ਬਸ ਚੱਲ ਪੇ ਚੱਲ ਪੇ
ਨਹੀਂ ਚੱਲ ਯੂਪੀਐਸ ਨਾ ਚੱਲ ਵੀ ਨਹੀਂ ਰਿਹਾ ਤੁਹਾਡਾ ਇਹਨੂੰ ਇਹ ਤੇ ਪਾਓ ਮੇਰੀ ਗੱਲ ਸੁਣੋ
ਚੱਲ ਪੇ ਯੂਪੀਐਸ ਚੱਲ ਪੇ
ਯੂਪੀਐਸ
ਫੇਰ ਰੁਕ ਗਿਆ
ਭਾਜੀ ਇਹਨੂੰ ਨਾ ਮੇਰੀ ਗੱਲ ਮੰਨੋ ਉੱਥੇ
ਚੱਲ ਪੇ ਬਸ ਚੱਲ ਪੇ
ਬੰਦ ਹੋ ਗਿਆ ਸਰ ਕੋਈ ਲਾਈਟ ਨਹੀਂ ਆ ਰਹੀ
ਬੰਦ ਹੋ ਗਈ
ਇਹ ਨਾ ਉੱਥੋਂ ਥੱਲੋਂ ਨਹੀਂ ਚੱਲ ਰਿਹਾ ਵੀਰੇ
ਯੂਪੀਐਸ ਉਧਰ ਲਾਈ
ਯੂਪੀਐਸ ਵਾਲੀ ਤਾਰ ਕੱਟੋ ਖੜ ਜੋ ਇਹ ਤੁਹਾਡਾ ਹਾਂ ਇਹਨੂੰ ਇਹ ਕਰਨਾ
ਕੋਈ ਤਾਰ ਵੀ ਨਹੀਂ ਚੱਲਦੀ ਇੱਥੇ
ਹੁਣ ਕਰੋ ਹੁਣ ਜਾ
ਚਲ ਠੀਕ
ਨਹੀਂ ਇੱਥੇ ਵੀ ਚੱਲ ਰਿਹਾ
ਚੱਲਿਆ
ਲੋ ਹੈ ਸਰ ਉੱਥੇ ਲੋ ਆ ਰਹੀ ਉੱਪਰ ਲੋ ਆ ਰਿਹਾ
ਲੋ ਤਾਂ ਇਸ ਕਰਕੇ ਆ ਰਿਹਾ ਨਾ, ਇਹਦੇ 'ਚ ਕਰੰਟ ਨਹੀਂ ਨਾ। ਇੱਕ ਮਿੰਟ ਇਹ ਸੁੱਚ ਚੱਲ ਰਿਹਾ, ਖੜੇ ਦੇਖੀ ਇਹਦੀ ਤਾਂ ਨਹੀਂ ਹੋਇਆ ਕਿ ਯਾਰ ਤਾਰ ਤਾਂ ਨਹੀਂ ਖਰਾਬ ਆ, ਦੂਜੀ ਤਾਰ ਲਾ ਕੇ ਦੇਖੀ, ਦੋ ਤਾਰਾਂ ਪਈਆਂ ਨੇ ਇਹਨਾਂ 'ਚ ਪਾਵਰ ਵਾਲੀ। ਹੁਣ ਦੇਖੋ ਵੀਰੇ ਚੱਕਰ ਵੀ ਨਹੀਂ, ਉਹਦੀ ਸਪਲਾਈ ਆ ਵੀ ਰਹੀ ਹੈ। ਲੈਪਟਾਪ ਚਾਰਜ ਇਹ ਦੇਖੋ ਪੂਰੀ ਚਾਰਜਿੰਗ ਲਾਇਆ ਜਿਹੜਾ ਲਾਈਟ ਕਰਕੇ। ਹਾਂ ਯਾਰ ਇਹ 'ਚ ਚਾਰਜ ਉਹ ਨਹੀਂ ਆ ਰਹੀ ਭਾਜੀ। ਹਾਂਜੀ ਇੱਧਰ ਲਾਈਟ ਹੀ ਨਹੀਂ ਆ ਰਹੀ।
हाँ
ਲਾਈਟ ਕਿਤੇ ਵੀ ਨਹੀਂ ਆ ਰਹੀ। ਸਮੈਲ ਆ ਰਹੀ ਹੈ, ਮੈਨੂੰ ਲੱਗਦਾ ਉਹ ਟ੍ਰਿਪ ਹੋਊਗੀ। ਇਹ ਮੈਨੂੰ ਲੱਗਦਾ ਇਹ ਵੀਰੇ ਜੇ ਕੋਈ ਪੇਚਕਸ ਹੈਗੇ ਨੇ ਸ਼ਾਰਟ ਹੋ ਰਿਹਾ ਇਹਦੇ ਅੰਦਰੋਂ।
नहीं आपने मैं पंजाबी यूनिवर्सिटी पटियाला से बोल रहा हूँ। आपने मेरे किया ना
ਤਾਰ ਕਿੰਨੀ ਕੁ ਹੁੰਦੀ ਹੈ ਆਪਣੀ?
टाइमिंग
ਤਾਰ ਹੈਗੀ ਸਰ ਆਪਣੀ
ਕੁਝ ਤਾਂ ਇਹਨਾਂ ਕੋਲ already ਹੈ ਨਾ, ਉਹਦੀ ਤਾਰ ਕਿੰਨੀ ਕੁ ਹੁੰਦੀ ਹੈ? ਆਪਣਾ ਬੋਰਡ ਹੈ
वो तो एक्सपर्ट
ਨਹੀਂ ਸਰ ਇਹਦੀ ਤਾਂ ਥੋੜੀ ਜਿਹੀ 2 ਮੀਟਰ ਹੋਣੀ ਬਸ।
ਸਵਿਚ ਬੋਰਡ ਨਹੀਂ ਹੈ
ਨਹੀਂ ਸਰ
ਆਪਣੇ ਕੋਲ ਟੈਸਟ ਪਿਨ ਵੀ ਨਹੀਂ ਹੈ ਨਾ, ਟੈਸਟ ਪਿਨ ਹੋਣਾ ਚਾਹੀਦਾ ਆਪਣੇ ਕੋਲ।
10
ਇੱਕ ਮਿੰਟ ਮੋਬਾਈਲ ਚਾਰਜਰ ਤੇ ਮੋਬਾਈਲ ਕੱਢੀ, ਉਹ ਸੁੱਚ ਦੇਖੀ ਤੇ ਚੱਲਦੇ, ਫਿਰ ਆਪਾਂ ਤੋਂ ਸਵਿਚ ਬੋਰਡ ਪਵਾ ਲਾਂਗੇ ਇਹਨਾਂ ਤੋਂ ਇੱਕ। ਇਹਨੂੰ ਲਾ ਕੇ ਦੇਖਦਾ ਹਾਂ ਆਪਾਂ ਨੇ ਇਹ ਕਰ ਲੈਣਾ, ਉਹ ਸਵਿਚ ਬੋਰਡ ਚੈੱਕ ਕਰ ਲੈਣਾ ਇੱਕ ਵਾਰ, ਪਰਲੇ ਵਾਲੇ ਦੀ ਘੰਟਾ ਆ ਰਹੀ ਹੈ ਤਾਂ ਇੱਕ ਰੋਜ਼ ਨਹੀਂ ਕਿਤੇ ਵੀ ਸਵਿਚ ਬੋਰਡ ਜਾਂ ਤਾਰ ਹੈਗੀ
तो होना ही है
ਇਹ ਨਹੀਂ ਕਰਦਾ, ਉਹ ਵੀ ਕਰੰਟ ਨਹੀਂ ਆ ਰਿਹਾ।
अरे चला के
ਇਹ ਵਾਲੀ ਸੌਰੀ
हाँ जी
ਹਾਂ ਇਹ ਚੱਲ ਰਹੇ ਨੇ ਸਵਿਚ ਵੀਰੇ, ਮੇਰੀ ਗੱਲ ਸੁਣੋ ਭਾਜੀ।
हाँ जी
ਹੈ
एक मिनट नहीं चला के दे
ਨਹੀਂ ਵੀਰੇ ਉਹ 'ਚ ਵੀ ਨਹੀਂ ਚੱਲ ਰਹੇ ਨਾ, ਉਧਰ
अरे चल नहीं रहा जी कोई भी ना
ਇੱਧਰ ਨਾ ਸਪਲਾਈ ਨਹੀਂ ਆ ਰਹੀ ਮੈਨੂੰ ਭਾਜੀ। ਉਹ ਚੱਲ ਰਿਹਾ ਤੁਹਾਡਾ ਉੱਥੋਂ ਦੀ, ਜੇ ਕੋਈ ਸਵਿਚ ਬੋਰਡ ਆਪਣੇ ਕੋਲ ਹੈਗਾ ਨਾ, ਤਾਰ ਜਾਂ
आ भी नहीं चल रहे
ਨਾ ਉਰੇ ਆ ਹੀ ਨਹੀਂ ਰਿਹਾ, ਕਰੰਟ ਹੀ ਨਹੀਂ ਆ ਰਿਹਾ ਨਾ। ਦੇਖੋ ਉਹ ਇੱਕ ਵਾਰੀ
नहीं आ बाकी चल रही है
ਨਹੀਂ ਚੱਲ ਰਹੀ ਵੀਰੇ, ਬੜੇ
बाकी
ਆ ਦੇਖੋ ਆ ਨਹੀਂ ਚੱਲ ਰਹੀ ਨਹੀਂ, ਉਹ ਚੱਲ ਰਿਹਾ, ਉਹ ਸਵਿਚ ਚੱਲ ਰਿਹਾ। ਜੇ ਆਪਣੇ ਕੋਲ ਕੋਈ ਉਹ
बड़े
ਆਪਾਂ ਨੇ ਤਾਂ ਤਾਰ ਲੈ ਲਈ ਆ ਥੋੜੀ ਲੰਬੀ। ਨਹੀਂ ਤਾਂ ਹੀ ਕਹਿ ਰਿਹਾ ਨਾ, ਉਹ ਸਵਿਚ ਬੋਰਡ ਤਾਂ ਉਰੇ ਚਾਹੀਦਾ, ਕੋਈ ਤਾਰ ਦਾ ਟੁਕੜਾ ਨਹੀਂ ਆ ਉੱਥੇ ਤੋਂ ਉਰੇ ਤੱਕ ਪਾ ਦਿੱਤਾ ਜਾਵੇ ਲੰਬੀ ਥੋੜੀ।
अपने मेरे किसी में चलेगा
ਚੱਲ ਜੇਗਾ ਸਰ, ਉਹ ਚਲਾ ਦਿੰਦੇ। ਉਹ ਨੇ ਪੁਆਇੰਟ ਨਾ ਉਹਦਾ ਤਾਰ ਸ਼ਾਰਟ ਹੋ ਗਿਆ, ਜਿਹਦੇ ਚ ਅੰਦਰ ਆ ਕੇ ਲੱਗ ਗਈ, ਫਿਕਸ ਹੋ ਗਿਆ। ਆ ਜਿਹੜਾ ਮੇਨ ਵਾਲਾ ਨਾ ਇੱਧਰਲੀ ਸਾਈਡ ਸਪਲਾਈ ਬੰਦ ਹੋ ਗਈ, ਇੱਧਰੋਂ ਟ੍ਰਿਪ ਹੋ ਗਈ। ਇਹਨੂੰ ਔਨ ਵੀ ਨਾ ਕਰਿਓ ਕਿਉਂਕਿ ਇੱਧਰ ਸ਼ਾਰਟਿੰਗ ਹੋ ਰਹੀ ਹੈ। ਜੇ ਉੱਧਰੋਂ ਔਨ ਕਰਾਂਗੇ ਆਪਾਂ ਇੱਧਰ ਉਹ ਹੋ ਸਕਦਾ ਖੋਲ ਕੇ ਕਰਨੀ ਪੈਣੀ। ਟਾਈਮ ਤੇ ਨਾ ਸਟਾਰਟਿੰਗ ਹੋ ਗਈ। ਆਪਾਂ ਨੂੰ ਕੀ ਕਰਾਂਗੇ ਆਪਾਂ
ਆਪਣੀ ਤਾਰ ਲੰਬੀ ਉੱਤੇ
ਆਪਾਂ ਤਾਂ ਬਚਣਾ ਨਹੀਂ ਤਾਂ ਉਹ ਸ਼ੁਰੂ ਕਰ ਦਿੰਦੇ ਹਾਂ ਪ੍ਰੋਗਰਾਮ ਹੀ ਕਰ ਰਹੇ ਹਾਂ। ਉਹਦੇ ਬਾਅਦ ਇਹਨੂੰ ਪਿੱਛੇ ਲਾ ਦਿੰਦੇ ਪਰ ਨਹੀਂ ਇਹਦੇ ਤੋਂ ਪਿੱਛੇ ਲੱਗ ਗਿਆ ਹੋਰ ਨਾ
ਸਰੀ ਨੋ ਕਰ ਦੇ ਇਹਨਾਂ ਨਾਲ ਕਨੈਕਸ਼ਨ
ਪਰਲੇ ਸੁੱਚਾਂ ਦੇ ਨਾਲ ਹੀ ਚੱਲਦੇ ਆ ਰਹੇ। ਇਹ ਚੱਲਦੀ ਨਹੀਂ, ਕਰੰਟ ਹੀ ਨਹੀਂ ਆ ਰਿਹਾ ਉਹਦੇ, ਕਰੰਟ ਨਹੀਂ ਆ ਰਿਹਾ।
ਆਪਾਂ ਆਪਣੀ ਤਾਰ ਹੀ ਉੱਤੇ ਲੈ ਜੀ
ਲੰਬਾ ਜਿਹਾ, ਹਾਂ ਹੁਣ ਬਣ ਗਈ ਗੱਲ। ਆਹ ਕੁੱਕ ਬੋਰਡ ਚਲਾ ਕੇ ਮੇਰੇ ਇਹ ਕਿੰਨੀ ਪਾਣੀ ਜ਼ਿਆਦਾ ਹੈ ਜਿੰਨੀ ਉਹ ਇੱਧਰ ਰੱਖ ਦਿੰਦੇ ਹਾਂ ਕਿ ਚਾਹ ਹੈ ਇਹ ਚਲਾ ਕੇ ਨੀਚੇ ਵਾਲਾ ਜਿਹੜਾ ਸੁੱਚ ਹੈ ਨਾ ਅੱਗੇ ਆ ਵੀ ਚੱਕ ਦਿਓ ਇਹ ਚਲਾ ਕੇ ਲੰਬਾ ਹੋ ਗਿਆ ਆ ਗਿਆ ਟਰੈਕਟਰ ਇੱਕ ਦਾ ਬ੍ਰੇਕ ਲਾ ਕੇ ਟਰੈਕਟਰ ਇਹ ਜਾਂ ਦੇ ਨਾਲ ਵੀ ਸਹੀ ਇਹ ਚੱਲ ਰਿਹਾ ਫਿਰ ਇਹ ਲਾ ਦੇ ਇਹ ਬਹੁਤ ਆ ਗਿਆ ਨਾ ਇਹਨੂੰ ਕਰਾਂਗੇ
ਇੱਥੇ ਰੱਖ ਲਓ ਬਸ ਸਾਰੇ
ਕੀ ਬਾਤ ਹੈ ਜੀ ਉਹਨਾਂ ਦਾ ਫੋਨ ਵੀ ਉਹਦੇ ਰੱਖਿਆ ਆ ਵੀਰੇ ਇਹ ਨਾ ਸ਼ਾਰਟਿੰਗ ਹੋ ਰਹੀ ਹੈ ਯਾਰ ਇਧਰ ਸਪਲਾਈ ਬੰਦ ਹੋ ਗਈ ਇੱਧਰ ਆਉਣਾ ਜਿਹੜਾ ਮੇਰਾ ਹੈਗਾ ਨਾ ਉਹ ਜੇ ਪੇੜ ਕਰੋ ਬੰਦ ਹੋ ਗਈ फिर कमरे जो हो जाएगी ठीक है
ਇੱਥੇ ਲਾਇਆ ਸੀ ਪਹਿਲਾਂ ਫਲੋਰ ਨਾਲ
इसी कर नहीं ये से स्पार्किंग है ਇਹਦੇ ਕਰਕੇ ਤਾਂ ਸ਼ਾਰਟਿੰਗ ਹੋ ਗਈ ਨਾ
ਫੋਨ ਹੋ ਜਾਏਗੀ ਦੂਜੇ ਸੁੱਚ ਤੇ ਹੋ ਜਾਏਗੀ ਨਾ
ਹਾਂਜੀ ਅੰਦਰ
ਹੋਰ ਵੀਰ ਜੀ ਹਲੇ
हेलो
टेस्ट बन जाएगी
हेलो हाँ बेटे क्या बोलो मुझे समझ नहीं लगा
मिनिस्ट्री वाले देखते हैं ना मॉनिटर करते हैं
It's never flown from home. Even
तो नाम लगता है
ਤੇ ਮੈਂ ਵੀ ਗੱਲ ਹੈ ਤਾਂ ਉਹ ਮਟਾਈ ਦੇਣਾ ਪੈਰਾਂ ਤੋਂ ਮੁਸ਼ਕਿਲ ਆ ਇਹਦੇ ਤੇ ਲਾ ਕੇ ਨਾ
remember.
It's a series which covers, we started in the 1930s. The first place, up to the 90s. Good period, he was writing books because he was an Amazon artist. Yes. That's very Hydrodynamic injection was naturalized instruction.
Biochemistry. Probably in the area of cellular life. But if assumptions are made to this type of activity, someone needs to it was not.
All the signals are reduced to that's the one that interesting.
Then
नहीं 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 ਤੁਸੀਂ ਆਇਓ
Now in the industrial field, there's a change of mindset, which is coming. It's what's
well, with voyages actually being able to do chemical measurements, it starts.
ਇਸ ਸਾਈਡ ਦਿਖ ਰਿਹਾ ਇੱਧਰ ਕਿਉਂ ਨਹੀਂ ਆ ਰਿਹਾ ਇਸ ਸਾਈਡ ਨਹੀਂ ਆ ਰਿਹਾ
Imaging is nice.
ਨਹੀਂ ਨਹੀਂ ਫਿਰ ਤਾਂ ਇਹ ਵੀ ਨਹੀਂ ਆਉਣਾ
fast imaging. The closer you look, the more heterogeneity you see.
बस सिर्फ ਇੱਥੇ ਲਿਖ ਰਿਹਾ एक बार और ये डिस्कनेक्ट
The
करें
hydrogen chains. Necessarily
करता ਸੀ मैं
Just not
पहले
the normal balance. Is it soil? Yes.
okay.
नहीं 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 एक बार स्टॉप कर तो सारा सारा कुछ स्टॉप कर दो एक बार स्विच ऑफ कर दो एक बार रीस्टार्ट कर दो कुछ वो तो नहीं है जस्ट लीव द कॉल
Yes. Now you hear me. Welcome back. Yes, let's do this. Thank you. So welcome back. Sorry, you didn't hear me. So I was going, just to repeat for the people who were there. I said that by changing, actually, by adding into the buffer some compounds which are going in interactions with the analytes, you are able actually to induce relative velocities of these analytes, and that's the separation at the end in the time you're looking at. So we're using from some cyclodextrins, which are actually some systems where you have a cavity, and in this cavity you have the possibility of binding of some components which have the right size, which have the right conformation, and that's where you are able actually to differentiate also optical isomers and enantiomers. And 3-point interactions. And we use this in different fields and different applications. And adding these neutral cytodextrins, for example, in the buffer, and inducing interaction, selective interactions of D and F and of the plus and minus forms of some pesticides, we were able to make the separation. That was, in the 90s, a very, very new way of going, because pesticides were at that time still applied as racemates in high amounts. And nowadays, we really go to the active enantiomer, which has activity to avoid any other effect of the other enantiomer in the environment. And we went into some applications that time were already coming out on chip, C on chip, which was used by NASA on Mars missions. Yeah, Mars is coming here as well. And also to separate the DNL amino acids. That's just some issues with LED. And this is, and that was some applications we are having that time, first time, and that impacted actually the pesticide community, because that time people were trying to see this effect, selective enantiomeric effect, in the degradation of pesticides in the environment. So that was an effect of soil quality on the behavior of racemates. Yeah. Anyway, you have your capillary and you add something in that is interacting. Next step in interactions, you add some micelles. Yeah? You may add some charged micelles in the systems. So it's not the natural cyclodextrin from before that are moving with the electrosmotic flow. Here you have micelles, so you can take SDS, or some kind of surfactants, which are creating micelles in solution in concentration higher than their critical micellar concentration. And these micelles in the system, they will move as well, depending on your setup. In this case, they will move to the left. The EOF is going to the right, so they move in countercurrent to the EOF, like the analytes, but in their way to the inlet vial, in this case, to the left, they will interact with compounds you may have added as analytes. These may be charged, but these may be neutral as well. So neutral analytes, which usually are moving with the AOF, in the classical case of zone electrophoresis, they will find their partners here, which they bring them on the way back, and which will separate them from the others as a function of their affinity. So as a function of their partition between the water and the micellar phase. Yeah? So that's actually what's happening here in the micellar mode. So micellar electrokinetic chromatography, MEKC. The word chromatography is coming in the world of electrophoresis. A little bit dangerous, but it's an interaction with something. That's probably why it came in. And that's a type of separation you may reach. This is a mixture of triazines, not the hydroxytriazines metabolites I was showing you before, where the hydroxy group is playing a role, but these are the neutral ones, the chlorinated ones, where some hydroxy is well as part of it, but that's mainly the chlorinated ones, and you can separate them as neutral compound in the system as a function of their partitioning between the water and the micellar phase. What can be used as surfactants? That's different surfactants. That's sodium dodecyl sulfate, SDS, and you see there is a critical micellar concentration at 8 millimolar with an average of 62 elements in this micelle. And depending on the structure and all the chemical changes, you may affect these surfactants, you may alter that and even generate surfactants which are specific in interaction with some of your analytes relative to others to induce selectivity. That's what we want in chromatography and in electrophoresis, in separation sciences. We want to increase selectivity. And you see already that here in the thinking, everything becomes possible as long it is compatible with the detection method to induce a separation. So use your fantasy to select and organize the partnerships between the analytes you want to separate in your capillary with something which may interact with. Can be an element, can be copper that is complexing, can be some complexing agents, can be some high affinity stuff, can be many things. So that was the start of thinking of using this cube and the solution in there as a reactor. Yeah? It's a reactor where reactions are occurring, which you are using to separate on one side. That's what we do here, actually with the MEKC, with the micelles, or to understand the process. Yeah? And especially MEKC is interesting for that.
Sir,
Yes, please.
what is the meaning of graph point?
Sorry?
Previous slide, graph point.
Oh, maybe. Let's. Craft point?
Yes, yes.
This is an excellent question. I could not respond now. I would go to Google and then I would look for it. What's a craft point? Do you know what a craft point is, Ross? Yes, I'm not alone not to know. Very good question. I'm sorry, I don't know. You put me on the wall now. No, I don't know. It's a good question. I need to check. If I put stuff on my transparency, I should know what I put on. You're absolutely right. Good. So that's how it looks in the capillary. Yeah. You inject on this side. The water as a marker of the EOF will come to the detector with the speed of the EOF. Yeah, so that's the marker you have. The micelles, they go to the other side. So they will move and they will have their own mobility as well in a way. Yeah? And the solute will be between the water plug and the micellar plug. Okay. And so that's actually how it looks like then in the chromatogram. Yeah? In time scale, you have the EOF, you have the solute, which may be a polyaromatic hydrocarbon, some kind of neutral compound, which is stacked between the water and the micellar phase as a partitioning. And that's actually what's happening here. That's another example with a separation. And this capacity factor, which is measured, which can be scaled as well, is showing you the partitioning between a fully micelle adsorbed 100% compounds and a fully non-in-micelle compound. And in between, you have the partitioning with a constant.
Philip?
Yes.
I've got a quick Google. The craft point is the minimum temperature at which a surfactant can form micelles.
Yes, thank you. So we go back to the table and we look at, so yes, it's, you see that's the temperature. Okay. Temperature dependent, makes sense. So you can even use this parameter in heating or not your capillary, depending on the surfactants you have. Maybe an idea. Yeah? Fantasy is open. Yeah, you can handle all this physical chemistry in this tube, and that's why I was fascinated that time. I did this in my PhD partially, and I discovered a world where, that's great. Yeah, engineering with thought before. Yeah, how can I use this system to have knowledge, gain knowledge, and in addition make separations?
If you link at that, we looked at one of those optical activated surfactants before we used mixing. I think you could use the craft point in the same way.
Yeah, it's a dimension. Yeah, like another. Yeah. Yes. So that's an idea. So you, again, you can use different pHs. That was with these hydroxyatrazines, which I showed you before, the behavior as cations and anions. And you can also calculate though the capacity factor along the pH range, being very high at low pH because these guys are cationic and have a strong interaction with the micelles and losing afterwards. So you can simulate it. You can simulate these things. You can make experiments and you can play with. Next step. CD MEKC. So having either a charged cyclodextrin that behaves like a micelle and moves in the system, or having a micellar system and you add in addition cyclodextrins, or any other thing that may interact specifically with one of the components. Yeah, I'm getting more and more complex solution in here. And that's what we tried here with a pesticide, which is called rulene, and which is a natural compound, and which we were able to separate using a micellar system with cyclodextrins. You can think of many things going on here. It's just that these are just examples. Yeah? And yes, this I crossed a little bit, but that was metolachlor that time with 4 isomers. This way we managed to separate 3 of them. And look at the buffer. There is some methanol, there is cyclodextrin inside, and that's how it's separated. Again, you can use it in an aqueous way or in a non-aqueous way. Also, it changed some properties of the components of the analytes, and in some cases, maybe radioactive. We went away also with metabolites from DDT. That was really an interesting issue in optimization, yeah, using some combinations of buffers, but managing to separate the autopara DDT and VDD at times. Some challenges you do, yeah. And that was one of my challenges. That's why I'm showing it. Very, I remember that time, which was very nice. And that brings us to the next step, which is actually bioaffinity seeing. Yeah? So having any type of component in the buffer that may interact and where you can bind with when you can make a partitioning and where you can calculate a partitioning coefficient in desorption of that analyte with what you're adding in the buffer. And that can be proteins, that can be DNA, that can be carbohydrates, and or that can be natural organic matter. That's the field I was coming from that time, from organic biochemistry. That can be anything in that behaves as a phase, and you look at the phase partitioning. For example, here, in adding some natural organic matter, so some soil extracted organic matter, into the buffer at different concentration, I was able to distinguish and to get our peaks out, in this case, of polyaromatic hydrocarbons, because it was moving into the phase. So always the same thinking. Again, using natural organic matter in the background buffer and using different amino acids, D and L, we were even be able to show that there is a selective enantioseparation, enantioselectivity in the absorption of the one form of the amino acid or the other, because this natural organic matter acts as a chiral phase. Think about it, many things can be done at this level. Plots here. That was an output, yeah, where actually we use different organics from different environments with different mixtures of different structures and functionalities, and we're able to have selectivity, structure selectivity in the binding of pesticides on this, or even DNL metabolites on that. It's even stuff which is not published, as I remember right now and seeing that. Yes. How is it done? Similarly, practically, you start with a measurement of the pesticide, of the components, with nothing added to the buffer, and then you increase the concentration of the ligand. Means on the right side here, you have here the concentration, and you have here the capacity factor, the partitioning, and you see it's going in the linearity. If you would use some micelles, you would be able to calculate here the critical micellar concentration. Means for humic substances, that enables us to calculate a concentration from which they behave as micelles, to have this interaction. Means in the concept of this strong complex material, the micellar model is one of them, and there are molecular aggregation that leads to this effect at some given concentrations. And based on this linearity here, you can calculate out the capacity factor. And that's very nice, because depending on having these pesticides with different matrices, you can calculate structure affinity issues and going to model and understanding the type of interactions which are specifically going on. That was done with triazine and binding to these different humic substances. We did the same with fluoroquinolones, which metabolites and photometabolites had different affinity to the soil where actually we had the study going on. And that also was excellent to go into modeling, because this binding constants we were calculated out, you can use them in modeling and understanding the behavior of pesticide in the soil column. So that's quite opening. Let's go to larger molecules. We did all with small molecules in separation, and larger molecules, it's interesting to see here, also from the empirical side, that these are polystyrene sulfonates with 1, 2, 3, 4, 5, up to 161 monomers. Yeah. So you have the monomer, oligomers, up to the polymer, and that's actually the effective mobility. So again, the field strength reduced velocity to be able to compare directly of the monomer, the dimer, the trimer, and so on and so forth. So you see that the more elements you put in your chain, the higher the mobility will be. Yeah, you will have accordingly an increase of the charge mass ratio, the charge size ratio. And from a given size, actually, you get a reverse effect to be stabilized at some point and not change anymore. So you get a stabilization. And this is coming because of a model where actually with counter ions, you have neutralization of charges in the middle of that building block, and the charges around the raspberries only contributing to the charge, the effective charge, which leads to the mobility. And that's the model which is here, where in terms of increasing the number of monomers, you first increase the mobility by adding the number of monomers with the maximum, and then you have some coil formation and some behavior like a raspberry. That's just a Manning's counter ion. Okay, I'll pause here. It's following some rules, and that's what we used here actually to explain that model. So I want to pass that because the time is going on to come to the next phase, which is capillary gel electrophoresis. So here you add, you increase the viscosity actually of your buffer by adding some physical gels. That's a possibility. Or by immobilizing a gel in your capillary. That's another possibility, having chemical gel. Means you have an hindrance based on size. And again, relative to a non-gel system where you have a mobility, you will have a change in mobility, which is how much it is affected due to the fact the size is there. And that's what we look. So it's a difference between the zone electrophoresis without gel and the gel here. And doing so and looking at this difference, you can go in a modeling. I will show you in a moment. So you have different entanglements with the physical gels, which enables you thus to be adapted on the type of separation you have. So concentration of these gels may affect and may do things. That brought lots of applications behind in separations of DNA and fragments and so on and so forth, and came actually the development of systems which were used routinely in this field. Different ways of behaving in the system with free solution. But at the end, if we take this polystyrene sulfonates, that was the one we had before, the 161 monomers and so on and so forth. So that's the without gel. If I put some gel in here at different concentration, I will have a separation and a change in separation and change in mobility. The higher change in mobility, the higher the mass. And that's actually what is plotted here. The higher the change in mobility and the higher mass, looking at the different gel concentrations. And like this you can model out actually and calculate back sizes. Applications in proteomics, in different fields, very early time already. Actually having some models with model compounds and then putting the unknowns, calculating sizes. That can go in further. You can separate particles, yeah? And you'll find many applications in separation of bacteria even, based on their surface charge. And people separate, collect them, and even cultivated them, yeah? So that's also possibilities. Other possibilities here, yeah, that's also bacteria which were well separated. And group in Torun, Buchowski, they did a lot of work on that 10 years ago. You can use and look at different reactions occurring in the cells. You can generate some films. You can alter the electrosmotic flow. You can really look at microbial exchange and behavior in the capillary. They're really an immense field of applications using these basic principles and applying them to different applications. So that's the fascinating thing in this field. Yeah, also here, if you have a gel, you can dot it and then with MALDI as a detection. Then you can try to combine all these different technologies of detection and mass spectrometry. Next issue, capillary isoelectric focusing. Definitely, it's possible. First, the capillary is filled with a sample, full ampholyte, gel, and the markers. Then there is a focusing stage, where the focusing is creating you the pH gradient in the capillary due to the ampholytes. And the analytes are positioning themselves in their mobility to the point where they are in zero charge. And because the isoelectric point is different, they will be positioned, and then you press them with pressure to the detector. That's the principle, which is very simple here. And that leads to this type of electropherograms with the focusing stage in the first minutes, and after a point of mobilization, where then the positioned analytes with their individual neutral points, isoelectric points, are coming out one after the other. B and C are two proteins, and here you can see that's simazine and amylin. That's the pesticides which have an isoelectric points, the hydroxysimazine and the amyline. Which I showed you before. They have isoelectric points, and you are able to separate these even small molecules based on the zero charge on the isoelectric points. Same is done, okay, with UMIX, with proteins very similar than we have it in gel. So you can go in modeling of that very easily, very pragmatically, to see that things. And here, that's just an example of separations in proteins. So many things are possible also to have different compounds or impurity. It's used in pharma actually to get impurity out and quality control. Many things have been developed in terms of detections to have detection all along the capillary with getting rid of the cover to be able to look inside with laser detection on capillary, etc., etc. Many development actually, which lead to applications or simply tries to put the method to the edge, which is important as well. Okay, we show that. We can measure isoelectric points, though, of the different analytes based on that, which is a structure information. Other way of complexifying is even to generate either a packed column with the particles, chromatography particles, or to generate the monolithic columns. When I was doing that, it was really the start of the monoliths, and we tried a lot around. And using these systems and having a separation based on difference of potential, electrokinetically, this is called electrochromatography, capillary electrochromatography. So if you would have the first system up here with the packed columns and put some pressure hydrodynamically, it would be called micro-LC. If you use this electrokinetically, it's electrochromatography. And again, here, a bunch of compounds can be separated that could not be separated with LC that time, or more effectively in shorter times, and with a high selectivity, even these polyaromatic hydrocarbons, and so on and so forth. Now you can combine also concepts. I mean, you can also combine capillary. You can combine this filled capillary with a capillary which is open, or you can fill and generate plugs of material in this capillary, and which can be used as micro SP, solid phase extraction. So systems where you concentrate your sample on, and then you wash it and you separate and you elute these concentrated samples from this plug in the capillary. Many applications are coming out of it. And that enables you to measure, you inject nanoliters, so you work really in the low microliter sample amount, and you have effectively detection at the end. It's a playground, but it's possible. Similarly, you will adapt the same system to microchromatography, just injecting a high sample plug into the beads, concentrating, and then having a separation in the second phase. So with a stacking like that, you are able actually to concentrate samples from 5 microliter solution into a little nanoliter plug, a few nanoliter plug, which is then separated. So you reach very high detection limits. This is in CMS as a detection. So bring you a little bit in that history, having the CE in front of the mass spec with all the problems of connectivities, because you need to have the separation voltage. So you need to have a high voltage gradient between the outlet and the inlet of the capillary where your sample is put, and you don't have to burn your mass spec in putting high voltages. So it's a little bit tricky, and there are different ways to do that. And especially this interface is of importance. So that's bringing me very nostalgically in my early career, where actually we developed these systems, and in a very practicable way, which now are sold in interfaces. But for CE, we have different ways to go, because you need to get contact before the MS, before the electrospray you have here, or the ionization method you have here. You have to have a contact in your column of the outlet to get the voltages through. Yeah. And this can be done either by adding another tube around where you get some liquid in, that's a sheath liquid, which is getting contact with the liquid in capillary to be able to put the tension. There is another tube around which usually is flowing gas to spray out and stabilize the spray. You may have systems which are in contact, which are liquid, well, this is also liquid supported in a way, yeah. But you have system which, you see the first approach here brings you a lot of dilution of your sample, and that has to be avoided. And this is why many applications tried actually to go and use some microelectrodes in there that to put the voltages or to some connectivities to get the voltages, which were more or less effective in their way. I will come at the end to what is done now, actually. And that enables you then the differentiation in time and mass, which is very important. We did a setup very practically like that, which worked extremely good. And the same setup is actually in the Agilent sprayer you can buy. It's the same. That came out a few years later, actually. Should have made a patent. Whatever. You have the sheath liquid coming in, you have the separation capillary, you have a contact with metal, you have the voltage which is applied, and at the end you have the spray, which is shown here. Usually we put camera to control it, and in very early stage of building up the systems, this is how it was looking like, with the camera, with the mass entrance, with all this stuff around on the stage, and with the micrometer you were able to adapt and adjust actually the positioning and adapt the voltages. Yes, I passed that. Again, that's some examples where we had applications with that's homoserine lactones and had nice separations and detection. However, that's the modern system. That's the Agilent sprayer, which is exactly the same principle and which can be used in different mass specs after the CE. Any type of CE, actually. And that's how it would look like. So that's what we set up in my lab with Agilent electrophoresis coupled here to the Agilent mass spec with ion mobility and the adjusted sheath liquid, which is pumped in to have the contact. The system, which is the CZMS, is sold by SciEx. Problem is it's effectively only compatible with these instruments. And this is a sheathless product, means there is no dilution by the contact liquid, but the sheath liquid, means you have an effective ionization at the end in the concentration it has, and very effectively. The problem is that it's an integrated system, it has high costs, and they work in having a porous system segment where actually they can have the contact done. And building up this thing is very costly, and if you break it, you can only drink beer because you're very your pocket is emptying with money, and so it's a little bit a problem, I feel. Yes, that's the kind of setup which it has with the cartridge. Also putting, I didn't say this at the beginning, putting a voltage around this liquid to get separation is generating heat. We had an lecture already issues on these aspects. What is done here, we have a liquid cooling around the capillary to temperate actually the capillary, the temperature you want to have it. And that's the setup though, with the coupling to the mass spec. Furthermore, things are moving, and now CEMS has a revival, definitely has a revival, because you separate analytes which are sometimes hard to separate with chromatography, and you can couple it with mass spec nicely in a routine. And papers came out actually using CEMS for metabolomics, for the profiling of polar metabolites of biological systems, and also using the mobility scale I was proposing before. So that's the paper that came out by some colleagues, and they evaluated that for metabolomics. And we recently, with Lisa and Michael, set up a package, in our package, where now you can do this automatically, because data processing is essential. And having a processing in mobility scale enables you this in the formats used to use the whole pipeline actually of LCMS mass analysis. At-line approach, just a little hint. You can also collect samples at the end, even though you're on the macro range level. And one of the possibility we proposed a few years ago was this. We use it's based on electrokinetic injection. Remember, you can inject hydrodynamically or electrokinetically. So what we did here is we took our sample, put it at a given pH, filled the capillary with the same buffer of that pH, and injected for a long time the whole capillary with electrokinetically. Means only the compounds which are ionized, which are present as ion in the sample, will move into the capillary. The neutral one, or the cations, or the one you want, they will stay in the buffer vial. So you selectively get out the compounds which are ions. Means at different pH, you will have different type of ions coming out, or different amounts of these ions coming out, depending on their range of ionization, depending on the pKa. At the end, when the capillary is filled after a while, we just push the whole plug into a vial, and at-line makes some direct injection FT or mass spectrometry. What we used are different compounds here, like benzoic acid, so having phenolic carboxylic groups, different numbers of carboxylic groups, also phenolic groups, or compounds which are fully charged and sulfonated, which have the same charge all the time, independent of the pH. And that's what comes out. So having different measurements of these compounds in mixtures at different pH of the sample at the beginning, having this electrokinetic injection. You see at low pH, you inject not much components, either they have a charge already, that's the sulfonated salts stuff, And by increasing the pH, you will see an increasing amount of some components to reach a plateau, and these are titration curves. So here I'm making titration of my known compounds actually in a few measurements. Again, I have the selectivity that enables me to get out components of different structures and different charges, which may be interesting if I want to get out of this solution only the sulfonated compounds. I can use the method and selectively get the sulfonated compounds by having a low pH electrokinetic injection. And I can calculate even the pKa. If I make more measurements, I can calculate bad pKa's, actually an unknown compounds of interest. That works quite well. And we use this for different, for organic aerosols on one side, but also on sample of interest. And these are wines. And in wines, we're interested, actually in wine, grape wine, we're interested in the sulfurization of metabolites, which are occurring during wine aging. Sulfur is added as an antioxidant and is reacting with metabolites there even more by time. And this way is an elegant way to distinguish sulfur-containing sulfonated compounds by having a low pH electrokinetic injection, collection, and measurements, and going into structural analysis with exact mass. So where do we go? So that was the part I wanted to show you. So you see it's a tube filled of liquid with more or less solvent. Push the analytes and you handle the behavior of the analytes by changing this solvent system, however you want to do it, compatible with the detection method. That's the beauty of it. So it's your fantasy that will generate the next methods in this field. Where do we go? Well, two-dimensional issues are of interest, and people are doing this, especially Christian in Aalen, Christian Neusus and his team. He's able to focus only on capillary electrophoresis, and that's really a great thing he's doing right now, and we do things together with his students, and that's a coupling, and especially the coupling enables a haircut approach, meaning to separate with the first dimension, and then you have a device, switching device, which enables you to cut you out part of these components you want to have, and bring these to the second dimension, which can be detected with mass spec. Means you can have protein separation, antibody separations in buffer which are not MS compatible. If you have micelles, it will not be good for your mass spec. If you have high ionic strength, neither. But by cutting it out of this sample, you have a dilution in the second stage, and it will be mass spec compatible, and you can add it. So they developed with the companies different systems in capillary size to cut out out of the mixture, the first dimension, to cut out actually the proteins and the peptides of interest. And that works very well. And it's coming into routine as well slowly, and industry has a lot of interest in that, to get impurities out of their protein synthesis, for example, in quality control. I won't tell anything on that because that's the purpose of the Giant course. I mean, definitely the further miniaturization, that's lab on a chip. We had a lot of talks on that. That's where it goes. Yeah? Using these principles I showed you in this big tube, which is a capillary relative to these systems. And many applications on chip which are electrophoretically based. You find them on the market. They are used partially in routine, more or less in routine, especially in the proteomic field. They are used in some cases. Okay, I'm at the end. So thanks for your attention. And if any question, send me an email. And for the people here in the room, I'm here in a week more and I will come back. So I'm glad to go in discussions. And in this simple system, just use your fantasy, yeah, and your knowledge in physical chemistry and chemistry, which are essential. Yeah, it's not only trying, but that enables you at least to set a frame and adapt this method to your need. That's the point. But the principles are simple and chemistry is behind. So thanks for that.
So friends, if you have any question, you can ask. Any question. Yes.
So can we use the capillary zone electrophoresis for the separation of nanoparticles?
Yes.
You are a very good question, but
Definitely.
we need. Should I answer?
Yes, please. I mean, you go ahead. Go ahead. No, you work on that definitely. I'm not working
No,
definitely on this field anymore, but principles, yes. You are really the expert, Ashok.
First,
Well, from the principle I showed, yes. And I suppose with entangled polymers in different concentrations, you may manage to optimize your system. But that's my theory. I haven't tried it, but Professor Malik will tell you because he has expertise in that.
yes, I
Please.
can tell you.
Yes, please.
More. Because nanoparticles, you mean metals?
Yes,
Yes.
such
and-
as titanium,
Yeah.
dioxide,
Yes. Yes.
or silver.
Yes, if you have like silver nanoparticles, good metal, you can separate them. This is true. Right? But problem is the detection. For this detector or atomic absorption means any detector which can detect your particular matters. Movement will take place in the capillary and after that you can detect. But problem is with the detection system and in analytical chemistry there is a paper and you can find separation of nanoparticles in analytical. Journal published by American Chemical Society, but it was a very nice paper, separation of nanoparticles, silver nanoparticles, very nice. But problem is with detection.
And
You can separate silver zero and silver nanoparticles. Silver zero, you understand? Means any reduced silver, which is in the atomic state, and nanoparticles, or any other, if you have some micelles, species, means depending on the size as the molecule, then this can be done. This is very good for thinking such.
Ashok, conductivity detection is possible?
Pardon?
Conductivity changes or indirect UV or stuff like that?
I never tried this, but this should be possible.
Because
But
maybe
these are
more reachable.
neutral particles.
Yeah. Yeah, so we need to put.
But if they are associated with micelles,
Could you pick up iron oxide with a magnetic?
they become charged. Okay? Means this is very.
It's fantasy. Yeah, that's what I mean with fantasy.
I appreciate your question and that it is kind of expensive. It is a very good research topic. So, nowadays it can be. But problem is instrumentation. Your name is? So I'm thankful to Professor Pele, Copley, and you know he's our friend, he's our boss, he's our anything. He's our friend, and so thank you, sir.
Thank you so much.
You can anything.
Do you want to move on now or after lunch? Because
It is.
we are about an hour behind schedule.
No,
I don't mind
actually,
that way.
please let me. We are
That
under
that was a team, huh?
You started 40 minutes late.
control.
It's not you.
We are under camera control and we are monitored by the MHRD. They are listening to our program and all over because we are on the YouTube also and they warned me at 11 your program is not started. When we were lucky.
So we'll do one now and one after lunch. I'm flexible.
Okay. You can start a little bit and after that.
No, we'll do the free flow like the freezes now. Let's see if I can find my movies. The download didn't work, so I downloaded the wrong files. So let's see if I can just run it from here. And then you can find the movies as well.
For about half an hour, and the rest we can
The rest we can then do later, so we'll see how far we get on the free flow. And then this afternoon will be a little bit of you guys just doing some stuff on paper. So the CE injection is more something you need to get your head around than where it's useful, where I'm talking for 50 minutes. Because unless you've written it down on paper, you're never going to understand it anyway. So we'll have a short one this afternoon where you guys will be doing something on paper. Maybe even I'll do some drawing on the blackboard. So we're going to go into another acceleration, and it's great that Professor Philip just introduced you to capillary electrophoresis and the greatness and the goodness of what can be done with it. And we're now going to dimension. So we've just done a loop or microchannel. There is no fundamental difference between doing capillary electrophoresis in a capillary or in a microchannel. If a microchannel is 50 micron and the capillary is 50 micron, it's a 50 micro thing, and the electric fields will do their best. So the technique electrophoresis doesn't care if it's done on something that's made in a clean room, in a 3D printer, or that it's a pooled capillary with a polyimide coating around it. So the technique, all the fundamentals, they all apply all the way across. And what we'll be looking at the current session is what's happening if we complement a hydrodynamic flow on top of the electrophoretic separation. But we don't do it in the same direction. So what we just heard about is having the EOF driving a liquid flow inside the capillary to be able to, for cations AE, still allow the anions that move in the other directions to still drag them along. Here we're going to have our electrophoretic separation perpendicular to our flow. So you can see in B, we've got a buffer flow coming down. I had a laser pointer earlier. Still do. So we can see that we've got a hydrodynamic buffer flow coming down towards us in the field of this slide. And we can see that a potential difference is applied across. Electrophoresis, the ions don't care, they feel a field and they start moving. It's like me and a heater, feel warmth and I go and move. So that's the field that the current presentation between now and lunch will be about. In the early days, free flow electrophoresis was really popular for fractionating protein mixtures. So they continuously infused the sample, plant extract, for example, in. So plant extract came in, it was a background electrolyte, potential difference applied, and then the fractions were collected. And in the 70s, 80s, a lot of the fractionation of different plant components is actually done by free flow electrophoresis. One of the challenges in free flow electrophoresis has been, and I missed Philip's first bit of the lectures, talk about joule heating? Little bit. Because if we get current in the system, we get heat being generated. If we get more current in the system, we get more heat. And at a certain point, heat becomes a problem because we get boiling. So these systems, while they were excellent to work with, one of the big engineering challenges has been to cool them down to effectively dissipate all the heat being generated during electrophoresis. Here we've got a movie that I'll play for you. That's not by itself yet. There we go. That's visual free flow electrolyte. Sometimes movies are just good to watch, and certainly late in the morning. So this is how the setup looks like. You can see a free flow electrophoresis cell, and then the tubes coming down into the fraction collector. So there's the...
Welcome to All Tech Lansing.
So here we've got the cell, which could be a PMA block. You could call it microfluidic, you could call then the electrolytes are being introduced. Then we apply it. We always do electrophoresis, which means that we get electrolysis taking place. So we need to have some buffering in place. And if the sample comes in, then the sample migrates in the electric field. So here we've got a collection of different analytes, and you can see them, the ones that have developed a high mobility in the electric field move far away. The ones that are not very mobile, not very fast, they don't move fast away. And so they keep on migrating, and because ions that are the same, have the same mobility, they will have the same force in the X direction. So although all the analytes have free flow electrophoresis, they experience at least two forces. One is the force going down in hydrodynamic flow. The other force they experience is perpendicular, and that's the electromigration force. So they all experience pretty much the same force going down the cell, going from the inlet to the outlet. But their deviation depends on their electrophoretic mobility. And then, as Philip already said, in electrophoresis, it then ends up on how creative you are. You can do free flow zone electrophoresis. Earlier we heard about capillary zone electrophoresis, having a normal background electrolyte. If we have our electric field perpendicular to our flow buffer, we have free flow zone electrophoresis. If you put an amphilyte in there, we can do free flow isoelectric focusing. And I thought you were going to talk about it, and we haven't, and I'm pretty sure we'll hear a lot more about ITP tomorrow. But ITP is isotechophoresis, where we go really creative and we actually don't have the same electrolyte at the front and the back of our analyte, but our analyte that sits in front of, or our background electrolyte ions that sit in front of our analytes are faster than those that are sitting at the back. And we then play a little game that you all have to move at the same speed, because you can't overtake the ones that are faster. So all the analytes move and order up in the flow in order of their mobility. So the fast ones can move very quickly all the way up to the point they go to the fast one, which we call the leading electrolyte. And the ones that are just a little bit faster than the terminating electrolyte, which is the slow coach in the family, will sit there. And then we can see here that the different fractions can be collected as well. So we can do all the different areas of free flow electrophoresis. We can, over all the different electrophoretic techniques, we can add micelles to a free flow cell, and we can do free flow MEKC. Why would we like to miniaturize free flow electrophoresis? And I already alluded to that. We've got joule heating. If we've got a current in an electrophoretic system, we generate heat. Heat could denature proteins, which isn't great. A bigger problem is that once it gets too warm, water starts boiling. If we've got boiling water, we've got bubbles. Bubbles are not really compatible with having a current in your system because they're perfect insulators. So if you want to destroy your electrophoretic separation, you put a bubble in there somewhere. So we want to reduce heat dissipation. There should be an H in there. With microfluidic system, we've had that higher surface to volume ratio, so we've got better heat dissipation. We can get easier get rid of our heat. The other advantage is that because we can miniaturize down the free flow electrophoresis cell from being 300-400 micron high to being only 50 or 20 micron high, which then also means that we've got less current in there, we've got less heat being generated. So win-win situation. Challenge, however, that we have is that we've got decreased throughput, because traditionally free flow electrophoresis was used preparatively, which means that you probably want to process reasonably large samples. Yes, if you miniaturize down, your flow throughput goes down. Could kind of address that going with parallel systems, but continuous flow separations are increasingly being sought after. And electrophoresis, I think we've got our projector is offset. Oh, it's not. Something with the computer. Smaller. So continuous separations are popular. Small means fast. And if we look at the free flow electrophoresis outcomes here from a microfluidic device, if I can get your little notifying thingy here to hide, can see that the separation times here in free flow electrophoresis are in the millisecond scale. So we can very, very quickly separate a mixture by free flow electrophoresis if we miniaturize it down. The other thing that we'll see in most of the examples we go through microfluidic free flow electrophoresis systems, some instrumentation, like for example mass spectrometry, they don't want an input in milliliters a minute, let alone in liters per minute. The throughput doesn't, with the miniaturization of a lot of our other instrumentation that we can do detection and characterization with, actually having a low volumetric throughput is not a problem anymore. With the mass spec, it's fine if you only have microliters or nanoliters a minute. If we want to do free flow electrophoresis and we want to design a free flow electrophoresis, which means that we get the formation of. We've already seen a lot of plots today that pH influences the electrophoretic separation. So pH changes we probably want to avoid if we're doing an electrophoretic separation, particularly while we're doing the run, because otherwise things in life get really, really unpredictable. The other thing, and I haven't put the little symbols with their faces in there, but we've got H2 and O2, which are gases. You've heard me say a couple of times that I don't like bubbles. So doing electrophoresis in any format comes with a couple of challenges. And if we do normally capillary electrophoresis in a capillary, as we've heard of this morning, we've got our electrolyte sitting in 2 little vials, and it's tucked somewhere deep in. The hydrogen and oxygen gas that are formed at the electrodes, they just bubble up to the top of the vials, and we don't have a problem with them. They just disappear. They'll find their way somewhere. And the volume, the 1.5, 2 milliliters that we've got sitting in those vials, is so large in comparison with the volume of the capillary that these pH changes are actually, if you use a good buffer, over the run of a CE, your pH doesn't noticeably change. There's a nice paper of Mirek Maka, I think in the mid-90s, who's actually visualized how much the pH changes if you wouldn't be buffering your CE system. So that's nice to look at. It's important in CE that you use a buffer because you don't want the pH to be changing due to your electrolysis at your electrodes. In a vial, it's not a big problem. If you start having a free flow electrophoresis cell that could be running for a whole day, it does become a problem. And then we've got the bubbles as well. In the very, very early days when I started doing my honors at the end of my undergrad, they got me to do some free flow electrophoresis. It was a project where we wanted to couple a CE separation to the mass spec, and we had some analytes that were not compatible with the mass spec. So we wanted to make sure they could be removed before we entered into the mass spec, which is probably one of the things that Philip said this morning. You can do anything in CE as long as it's compatible with your detector. If it's not compatible with your detector, you may be able to remove the incompatibility and still use the detector that you initially chose. So what I developed was a big PMMA block of plastic. I defined my separation chamber by having a bit of parafilm. Parafilm is about 200 micron thickness, but if you squeeze it with some screws, it comes down to around 100 micron. These days, I probably use a laser cutter, but in this, we're talking 98 here. So I only had a scalpel. So I cut the dark green shape here out of parafilm. There were some screw holes sitting around there, bolted down. These were bits of filter paper to provide some hydrodynamic resistance to prevent too much exchange so to prevent my buffer being pumped in here to leave through my electrode chambers. And these were electrode chambers that were a little bit deeper to get a little bit more buffer capacity, and they were used at 10 times the concentration to my background electrolyte used here for the separation. Means that I got the same chemistry, I got a higher buffer capacity, and I could use a low buffer capacity buffer for my free flow electrophoresis, which kept the current down, which kept the joule heating down. So yes, in my honors in 98, I did microfluidics. What did my whole setup consist of? 2 blocks of plastic and a bit of parafilm with some bits of filter paper in the middle. Again, if I want one thing to get across to you, microfluidics is not out of reach if you don't have a clean room. There's a lot of things that you can make up with what you've got hanging around, particularly if you've got a mechanical workshop somewhere in the vicinity that you can access. A little bit more advanced device than what I just talked about. I'm not sure how we can actually get the whole device into focus. Well, I can get by with this. So this was published a couple of years ago. Again, a free flow electrophoresis device where we've got PDMS, the squashing material I had yesterday. PDMS slab, again, membranes being used to increase the hydrodynamic resistance between the electrode reservoirs and the area where the free flow electrophoresis actually took place. This PDMS slab was put onto the glass and then sealed again with another glass chip. And this is where you can see the assembly together, where you've got the bottom glass, the PDMS, and then there was the top glass. You can just see it here in the one that's dropped off. What was very nicely done in this instance, because you can see the platinum wire here sitting along to apply the potential for the separation. What was nicely done here is that this chamber here had an inlet and an outlet, and electrolyte could be continuously perfused through the electrode chamber, which meant that the bubbles as well as the electrolysis products could be continuously removed. And then the outlets could be connected to a 96 well plate to do the fraction collection. The Belder group came up with another solution. In this instance, it's a PMMA, so it's a plastic microchip. From memory, it was even made by the chip shop. As you can see, they didn't use the filter paper for the hydrodynamic resistance, but they used microfabrication to create a really shallow, high flow resistance connection here. So the whole chamber itself was 50 micron high. Here there's only a 20 micron gap, which has got a higher flow resistance, which means the vast majority of the flow will go straight because there's a higher resistance to flowing out through the electrode chambers. You can see nicely that they'd integrated electrodes in there, so they didn't need to try to fiddle in a platinum electrode into the reservoir. The electrodes here were integrated into the device, and the electrolyte reservoir was open to the open air, which means that the electrolysis bubbles with the hydrogen, the oxygen gas, could just go out into the air, and there was little to no risk that these bubbles would make it into the free flow electrophoresis chamber to create havoc. And you can see a nice separation of a couple of different food dyes here, where they come onto the inlet here, and you can see them being spread around according to electrophoretic mobility. More recently, an article got presented where they used free flow electrophoresis in combination with the mass spectrometry, and they had different outlets, as you can see here, and they were connected with a selection valve. And the selection valve decided which fraction was being injected into the mass spectrometer. So you can see electrophoresis cell. This is the direction where the hydrodynamic flow goes. Electrophoretic separation happens perpendicular to that. They had AMP, acetyl-CoA and ATP in there as analytes. You could see they could separate them into the different fractions. And each of these, using the selection valve, they could decide, we want to now look at the mass spectrum from fraction 1, fraction 2, fraction 3. And here you can see that AMP came out in fraction 3 at the end of the cell. CoA came out in fraction number 4. And we saw our ATP coming out in fraction 1. So you could continuously fractionate a mixture by free flow electrophoresis, and then use a selection valve to look at a single fraction at a time by mass spectrometry. Free flow mass spec was also used again by the Belder group, and they've been doing a fair bit of the free flow electrophoresis. And what they did here is that they had an organic reaction going on, and they continuously fed the reaction product into the free flow electrophoresis cell, where they could get a separation of the starting compounds as well as the final product. And using mass spec at the outlet, they could follow the progression of the organic synthesis reaction using an initial sample preparation, pre-separation in real time by free flow electrophoresis. I thought Phil was going to be talking about isotechophoresis, and we haven't. So the next one that I'm going to show you is doing some isotechophoresis in the microfluidic device. So I already told you that isotechophoresis has got a leading electrolyte, which is faster than the analytes, a trailing electrolyte, which is slower, and your analyte you pick you pick your leading and trailing electrolytes based on the mobility of your analytes, so that they sit in the middle and stack up there. Normally in isotechophoresis, you get plateaus being formed because your ions are present in relatively high concentration, and they will stack up here as a plateau. Because their mobility is lower, their conductivity is a little bit lower as well. So they'll stack up here as a slightly lower conductivity profile, one after another, up to the point you're at the terminating electrolyte, because we want to equalize our current in the system. We can't have a high current in one part of the system and a low current in the next. It's a continuous system, and that's why we're moving at the same speed. There is a little bit of a crisis happening, though, in the electrophoresis system if our analyte concentration is really low, because then we've got that mobility compound that would like to carry the same current as is going through the leader and the terminator, but it can't, because it's not in high enough concentration. And what happens is that analyte then gets squashed between the leader and terminator to just still maintain that current profile. And that's called peak mode isotechophoresis. So instead of having a plateau that gets longer and longer with increasing concentration, we get all the analytes squashed in a very, very small space between our leader and terminating electrolytes. And that's called peak mode isotechophoresis, and is a very nice way to selectively concentrate particular analytes based on their mobility. Because any analyte that doesn't have a mobility between your leader and your terminator is going to be dissipating out because it doesn't fit into the mobility gap, the mobility window that's created here. So you can very selectively isolate one or a very small group of analytes by picking your leading and terminating electrolyte, only providing a very narrow window there. So we were thinking about some limitations of the isotechophoresis as an analytical technique, because it sounds great that things stack up in the order. But I've already said that the peak length is determined by the concentration, which means that the good thing that we like in analytical chemistry, that we can identify a compound based on their migration time, that advantage is no longer there. Because if we've got more of the third analyte in a row, all our times after analyte 3 will change, because that one will just become a much longer zone. So the quantitation based on length and not height and area, the fact that if your sample composition changes, all your migration times change, make data analysis challenging, hard to automate, difficult to interpret, and therefore not really attractive to be used as a standard analytical technology, because no one likes difficult. What we were thinking about, and I'll now be moving from the specific examples of free flow electrophoresis to something that I've done a couple of years ago, 2014-15, is try to do a very isotechophoresis in the free flow mode. So what we had is having a free flow electrophoresis device with our leading electrolyte and our terminating electrolytes, and then our sample coming in to do isotechophoresis with. To kind of get over the fact that the position of the peaks was going to be changing depending on how what the composition of the sample was, we realized that we've got a great tool in microfluidics. We have a pump that's anyway driving the electrolyte from the top to the bottom of this free flow electrophoresis cell. Which means that if you want to have your analyte always coming out in this outlet because that's connected to your mass spectrometer, you can actually use your control flow. You can use the difference in the ratio between your flow that's sitting here, your leading electrolyte flow, and your terminating electrolyte flow, to position your analyte at the outlet that's connected to your mass spectrometer. And I'm hoping that the movie... So this is how the device looked like. So we have a free flow electrophoresis system. We've got side chambers for the electrodes. We've got the sample coming in, terminating and leading electrolyte. We've got outlets where one of them was connected to the mass spec, using an electrospray interface. You can see all the little dots here. They were little pillars to keep the roof up. This was a chamber that was, I think, 5 centimeters wide. That's 2 millimeter scale bar. It was reasonably wide. It was 20 or 30 micron high. The first try that we did at this was making it without the pillars, and the glass sagged down, and we actually didn't have a chamber anymore because the top and bottom were touching each other. So we've got a whole support network here of little posts in there to keep the roof up so that we could continue to do our electrophoresis. They didn't participate. We didn't use them for any interaction. We didn't functionalize them. They're just there holding the roof up because otherwise the chamber collapsed. So this is the system that we were working with. So we had formic acid as our slow coach, as our terminating electrolyte, propionic acid as our leading electrolyte, and we had a mixture of fluorescein, Electrofluor, and citric acid. 2 of them are fluorescent. The other one we just say that's the one that we can't see. They are analytes that have fairly similar mobility, but except for the fluorescein, which is a bit faster. So we've got the mobility of fluorescein is faster than that of propionic acid. Electrofluor and citric acid were reasonably similar, and the formic acid was slower. What happens if we put a potential difference across this is that our fluorescein is faster than a propionic acid, so it swims away. It's not part of the window. It's not welcome. So that was one of the things that we want to present. If we've got an analyte present in our sample that we really, really don't want to have in our mass spec, not that fluorescein is bad, but it's visible, so that's why I picked it here. You can actually get rid of one of your analytes if its mobility under your separation conditions is not inside your ITP window. So we picked our ITP window here so that fluorescein wouldn't fit in, and we could get rid of the fluorescein. It just dissipated into our leading electrolyte. So we were left in our ITP focusing zone with citric acid and Electrofluor, and the formic acid sitting as the terminating electrolyte behind it. We'll be talking a lot more about simulation of ITP tomorrow. But this is an example on how the simulation looks like. Here we've got in pink, we've got a propionic acid, which is our leading electrolyte. We've got our citric acid and our Electrofluor as our 2 different analytes being focused up. And then we've got our terminating electrolyte. And we can see the little bump here of our fluorescein that isn't welcome. And by the time that this separation is run, by the time our analytes have migrated from the top to the bottom of the cell, as we'll see later in the first centimeter, all our fluorescein will have dissipated. So that's the simulation of the separation that we wanted to be doing in our free flow electrophoresis chip. This is where it's going to get scary to see if we can actually get the movie to work. No, we can't get the movie to work. So here we can see that when we increase the flow rate, we can change the position where our analytes focus, which gave us the confidence that we can actually push things up and down. And we could quantify that. We could very nicely clean out the fluorescein. So we could remove the fluorescein from citric acid. That was our analyte, doing ITP as a sample prep step before mass spectrometry. Lucky I didn't only rely on pictures. So this is how the system looks like under the microscope. So you can see the little black dots that are the pillars. Here you can see the width of the sample stream, the way it's coming in. It's getting exposed to the electric field, so we get the isotachophoresis taking place. So you can see how much it concentrates from the low concentration of fluorescence you can see here. We can see here the Electrofluor doing, and we played around with the concentration that we were just in peak mode. So you can just see a very high concentration of the fluorescent dye forming straight behind the leading electrolyte, which demonstrates the very nice focusing of effects that you can do with electrophoresis. And I think that's one of the things what I appreciate most about the electrophoretic technologies. They don't only allow you to separate things and dilute them in that way, they're also really affecting, enhancing concentration. And if you want to separate molecules, you quite often risk that you everything you do with them, you dilute them further. And that means that you need to push your sensitivity of detector higher and higher. This is a very nice way of focusing things. And focusing is good because you get more of what you want in a very small volume. Here's some mass spectra. Well, the selected ion electropherograms are kind of dropped off. But here we can see the different M/Z ratio, where we've got the fluorescein, hardly detectable because it's all dissipated. And we can see that the glycolic acid and the citric acid were nicely separated. And we could see that by moving different fractions of our ITP zone around in front of our detector outlet. Another thing, and this is the last part of the free flow electrophoresis that's nice about microfluidics, is that you can daisy chain things together. So this is a two-dimensional free flow electrophoresis system, where here we've got an inlet. We do our first separation. We then split what we get out into 3 more dimensions, where again we do a free flow electrophoresis separation. And what we've learned in analytical chemistry in general, you can't separate anything that you want to do in one column. But if you combine different analytical dimensions with one and another, if you pack them clever enough, you can actually multiply the resolution that you can achieve. So if you want to separate a very complex medium, getting there may be a lot faster if you use complementary separation methods, rather than just getting a longer and a longer and a longer LC column. So that's a nice way that by doing some plumbing in microfluidics, you can actually do multidimensional separations as well. Ready for lunch. So I hope this was brief enough to keep you from lunch. And yeah, we'll do some hard stuff this afternoon, trying to get our heads around how ions move. We'll test through you with some cations and anions, doing different kinds of electrokinetic injections from chips. Trust me, you'll get your head around it. By the time you've got it all written, you'll never forget it. So it's like learning to ride a bike this afternoon. Enjoy lunch.
So please be
There we go. So you can see just the fluorescein running away as soon as the voltage goes on.
Excuse me, I have a question. Why is there only hydrodynamic flow electrophoresis and not electrosmotic flow?
I didn't want to confuse you any further. Normally, you put an agent in there that stops the electroosmotic flow